Hi, welcome to making a game engine with Godot feature using standard C++. My name is, thank you. So my name is Raphaël. I'm a gamer at heart. I'm currently studying at Sherbrooke University. It's near Montreal in Quebec, Canada. Currently doing an internship at Audio-Kinetic. So for the context of our student project, we were a team of 4. We had average C++ knowledge, meaning like we knew what a destructor was, we knew like the rule of 3, how to handle pointers, but we didn't knew much about like smart pointers or like move semantics, and other things like that. So it was like a kind of a huge challenge for us. And we started, all teams started from the same baseline, I would say, which is called in French Petit Moteur 3D. I had to say it. In English, I would say PM3D. So PM3D, for short, to be short, it's like Learn OpenGL, if you know it, but for DirectX 11. So it guides us through making like our first cube, and then like putting a camera in the scene, things like that. So yep, and we had milestone to guide us throughout the semester, which the project duration was between 24 months, which is like pretty much the overall semester for us in Canada, at least in Quebec, I would say. And yeah, so we had between 3 and 4 months, but we also had other classes with the infamous AI class too. We had to use Windows DirectX 11, and we had to use a physics engine. Jolt was like highly recommended, and we all end up using it. And we had to make a racing game, essentially, using that small engine. So I'm just going to show like a very quick video, hoping that I still have time at the end for the rest of my presentation. So you can see here, we choose to make like a snow mobile. We thought it was super fun. There's lights, shadow maps. You have UI on the bottom left. The camera can switch between a third person and a first person. We're going to see like in 1 second. That's pretty much it for the game. I'm going to focus more on the engine side. So sorry, PM3D, we kind of move away from you. Objects were having like too much responsibility in this architecture. It was hard to do like composition, and we just wanted to try something else, roll around thing. We're at university to learn and try new things, so why not? So we got inspired by Godot. Godot is a game engine, which is popular, I would say. At least on same level as like, maybe not on the same level, but as Unity, like on Unity and Unreal, and is infamous for its node and scene hierarchy. We implemented something very similar, which you're gonna see in a second. It's also popular for its. There's also a signal system, which is like pretty central to how you do gameplay programming in it. The signal system, is the observer pattern implementation of Godot. And Godot also have a Jolt integration, so I guess that's make another point similar to us. So for Godot's hierarchy, that's the real Godot hierarchy right there. That's a screenshot. That's like the latest version. So, I mean, there's way more objects, obviously, but I kind of filtered through it. So right now, on the top level, you can see you have a node, which is like your base object. You have then node 3D, which means like an object with a 3D position. And then you have collision object and all the children's, which are essentially physical object. Physical, when I mean physical, I mean physics as in physics, physics simulation, like body, like collisions, things like that. And then you have visual instance 3D, which is like for like visuals. So hierarchy is pretty similar, as I said. We have a node on top, node 3D for a 3D position, node drawer actually, but So we have a node drawer which handles all the DirectX 11 things, and the hierarchy of each of these nodes down there, like of each of the leaf here, it goes even further. For example, drawer, we have like a model. We have another node model which loads a model and like makes the rendering on screen happening. for the model. And we have Node Collider, which is responsible for interacting with our physics server, actually, which I'm going to show later. So for the node, each node has a pointer to its parent, except except for the root node, it has a null pointer essentially. Each node is responsible for its children. So each a child node is necessarily a unique pointer, and it is contained inside a vector. And each node have a unique identifier, which is like very useful. We use it in many cases for example, the destruction. So our node interface goes like this. It's pretty standard. Like if you know typical game engines, you have like update 3D, updates like our loop, destroy. We're gonna talk about it a little bit later. And remove and attach is what we use to like link node together. So you may have seen like, hey, that's kind of weird. Like you're using like a R value reference right there to attach the nodes. Yeah, it's because we want to be very explicit about ownership when programming, at least in our framework that we made. So what I mean by that is every node in our system is a unique pointer, and if you want to like attach nodes together, you have to actually move it. So when you with the signature, what we are actually trying to say, at least, is, hey, I'm giving you the responsibility of the node that I'm giving you. So each parent node is responsible for its child node, and when it gets destroyed, it will destroy automatically all of its children node. So here, destroy actually respects RAII, which is difficult to say for me. It's not like a C thing where it's where we do manual memory management. It's really just marking the node for deletion for the next frame, essentially. And upon the next frame, we go through the sync tree through the nodes. And then when we know that the nodes must be destroyed, we just swap it with a null pointer, erase it, and let the unique pointer does the job. So it's very easy, like to both read the code, I would say, in some sense, and like understanding, like making sure the objects are properly managed. So here for remove, I just want to say, like, we didn't know about algorithm when we started, and it was really great. We use it across all the code base right now. So here is just a find if. It's pretty simple, but hey, that's when you start using algorithm, that's where you might start to. And it was very nice for us to just like it was using that made our code more declarative and clear. So I'm going to move to the observer pattern here. So we have event signal. So it's not a signal, it's an event signal, right? It has a template parameter pack, if I say it right. So here params is the template parameter pack, and we params defines what are the params of the callback. So we have two aliases down there, which is we have a callback, which is essentially a standard function, which takes some params. The params defined by the event signal. It was really useful for us to use a standard function. Like you could pass lambdas, you could pass, I don't know, man, a pointer to a function, member function. You could pass anything to a standard function. That was really great. Using signal, that's the alias for like an observer. So it's a pair between the node ID, which is unique, and a callback. So when a node connects to a signal, it gives its node ID and a callback. And we have a list of observers for the event signal. So here we can see like the logic for, we see the logic for the connection. So what would happen is like you would take a signal, we would have a signal, for example, on it. We say on it.connect, pass the node, pass the callback, boom, that's it. Observer pushback, that's where it happens. For the disconnection, again, pretty simple. I'm just gonna skip through it. And for emitting, that's where the magic of the pack happen. We just take the params and pass it. We just have to make sure that the signature is good, and then you can just call all the callbacks that were registered. I just want to insist on the fact that that template pack was very useful for us, because we have events, for example, when we change levels, we change from the main menu and the main level, or we have events, collisions, and other kinds of events. So not having to always define another event signal for each specific case was a huge gain for us. And also, the signals are like, they work hand in hand with the node system. So when a node is destroyed, the disconnection happens automatically, which is kind of nice. So for the Jolt integration, we really try to keep it as simple as possible. So I hope it will be clear to explain. So here we have the node collider. If you remember from the hierarchy, it's the one responsible to register a body, for example, to the physics server. A physics server is simply like a wrapper or a facade, depending on like how you see it, to Jolt. And then the physics server registers collision to the mailbox, and then on update, when we are updating the game, the node collider consults the collisions from the mailbox. So here our mailbox is essentially a singleton. I'm just gonna skip through it for making sure we have time. Okay, so our physics server. So we see right on top the subsystem. That is what is wrapped by our physics system. Our physics servers. So the physics server wraps that subsystem. So right on top, we can see we have some data that is related to our needs. So we have bodies, we have raycast, we have bodies that we want to activate, bodies what we want to deactivate, things like that. And we have also like overrides, because in Jolt, you have like to configure, the subsystem, and when you're configuring it, you have to pass essentially like your implementation of certain classes. So here, for example, right at the bottom of the blue square, we have the contact listener. Each time there was a contact in the game, there was a callback in the contact listener that would get called, and from there we would register the collision to the mailbox. So the physics server like has a couple like of methods for ease to use, so adding a force, adding an impulse, registering a body, launching a raycast, a couple of things like that would kind of wrap around our usage of Jolt. So here's the main the stepping function, which is like the update for the physics server. I thought it would be like kind of cool to see, like normally we don't see that kind of thing. So we can see like before we remove the body, actually before stepping, and we add the body afterward. I hope that's a good way to do it. At least it worked for us. And we do our raycasting right there. I'm gonna talk a little bit about the raycasting, because there are a couple of C++ thingy that I thought was simple yet cool to talk about. So for example, just the optional right there, like in game engines, in games in general, there's tons of like situation where you actually don't know if you have the data or not. Like for example, here for the hit, we don't know if you actually got a hit. So I'm protecting myself from Raphaël coding at 3 a.m. forgetting to check a bool. Is the thing set? So now I have to check it with SCD optional. I can't, I have to take responsibility. And for the raycasting share ownership, we use actually a share pointer here. So that's one of the few instances actually where we use a share pointer. And the reason we do is because we want, let me rephrase it. like the hit is shared between the physics servers and the raycast. And the physics server may need the hit, and the raycast may need the hit too. But we don't know, like, for example, the physics server may not need the hit anymore before the raycast, or we don't know which is going to be the last owner, essentially, of the hit. And using a share pointer just solved that problem for us. It's very specific, and it makes the intent more clear when you don't overly use it, in my opinion. And we use make share, and I think you should use it if you're like, if you can. So we also have an editor, real quick. It does some pretty simple stuff, endless transform, pausing the game, moving objects around, was pretty useful. But the editor, I just want to say, it has like a ton of functions that are like kind of similar to like metadata, I would say, almost. So there's a ton of code that you change that you didn't know you would need for the editor to work properly. So if you plan to do an editor, like really think through it before, I would say. And yeah, it was super useful. And being able to identify resource with a unique ID in the editor was like a lifesaver for us. And our main CPU hurdle, I gotta say it, was the building system. So if we knew about CMake more before starting out, that would have really helped us. Or about VC package too. There's a ton of things we didn't cover, like light shadow map, pod process, native UI using DirectX, camera and strategies. Like, of course, it's a game engine. I have 15 minutes, and I've already got over. So in conclusion, we learned a lot. It was a great challenge, and C++ is very cool, and the usage of modern C++ really simplify our code. Thank you.
Thank you. That was really nice. Next one should be Dennis Gusti.